The following, I guess, lectures, if you look on the page, are in a colossal sort of multi-hundred-page set of slides. That's, I guess, partly for latex compilation reasons, but also partly because I think there will be a consistent theme in the next few lectures, which are about basically how to represent probabilities in feature space. So what we talked about for the first two lectures was how to represent single points in feature space by and large, and what it meant for sort of functions of points. So in the next, I guess, 3 or 4 lectures, I'm going to be talking about how to represent probabilities in feature space and what one might be able to do with these representations. So I'm going to begin by a relevant motivating example, which is how do you detect dependence between two random variables when these are discrete valued? So what do I mean by discrete valued? Well, let's say here are my two binary random variables. So one is that I remember or not to set my alarm in the morning, and the second is I'm late or not late to a lecture. So I want to know whether there exists some relationship between these two binary valued random variables. So as a good frequentist, how would I do this? Well, what I'd do is I would repeat the experiment many, many times. So I would forget or not to set my alarm, and I would determine whether or not I'm on time. And I would then fill this table of joint probabilities by just dividing the number of times these two events happened together by the total number of times I repeated the experiment. And so I get this table of joint probabilities of me remembering or not to set my alarm and being late or not. So this is real, if no. Anyway, and so then I want to know whether this is a real relation. So I compare this with the product of the marginals, which is what I would get under the assumption that there was no link between being on time and late. And you can see already from this table that even looking at the joint probability, something's not right here, because my joint probability of no alarm and on time is actually higher than my joint probability of alarm and on time. So intuitively, there is a problem. But what I want to do, I guess, to formally make a statistical test of whether the dependence between alarm and on time is significant, is that I use some distance measure between these two tables. And if the distance between these two tables is large enough that it can't be explained by chance, then I decide that there is in fact a significant dependence between the two events. Okay? So this is, if somebody was sort of asking you how to solve this problem and you looked up a classical statistics textbook, then this is the kind of thing that you would use to solve it. Okay? So this is fine, but the trouble is that you can find situations that break it. So here are here is a draw from two discrete valued random variables. So here is like 8 lines of English and here's 8 lines of French. And imagine that I have a distribution that's generating these two pairs like over and over. So like I've got 100 examples of these pairs of documents. And I want to then ask whether the French text is dependent on the English text. So is it the case that these two are translations of each other? Like you've seen lots and lots of examples. Is it the case that you can determine that there is a strong dependence between the English text and the French text based on all of these examples? Now the problem is that if I then looked up my statistics textbook and I said I want to make a joint probability table of all of the 8-line English extracts and the corresponding 8-line French extracts, and then I tick a box every time I see a particular pair, well, this table is like many kilometers long and I have almost no boxes ticked. And it would take me a lot of samples to determine whether there exists a dependence between the English and French text. So it seems that this sort of classical approach to the problem is not one that's going to solve it, at least for these more complicated kinds of discrete valued random variables. Okay? So here is another example, which is, in a sense, sort of even higher dimensional than discrete, which is if you have continuous valued random variables. So let's say that you've got x, which is now continuous valued, so it can take infinitely many possible values, and y, which is also continuous valued, so it can take, again, as many as infinite values. And I've drawn a sample from pxy, so I've drawn a set of points from some density. And I want to determine whether there is some relation between x and y. So just looking at the picture, I would say yes, because like knowing x tells you something about where y is. So if I know that x is 0, then y is either -1 or maybe 0.3 or something. And if y is -1, then I know for sure that if x is -1, then y is -0.4. So there is something, there is information about y and x. But I want to test, I want to find some statistical test of whether there is a significant dependence between these. On the basis of the sample that I've seen, can I say that there exists like a significant link between x and y? Okay, so what this amounts to doing is testing again whether this distribution is drawn from something like this, so this is the joint distribution, or something like this, which is the product of the marginals, which is what the density would look like if x and y had the same marginal distributions but were independent. Okay, so you get an even worse problem on the previous slide, because now x can not only take a huge number of discrete values, it can actually take infinitely many values. But how do we actually go about solving this? Well, you can start by reducing it to the problem on the previous slide. So what I would do is I would partition my x space, I would break it up into bins, I would partition my y space as well, and then I would count the number of points that fall in each bin. Okay, so then I would get this joint distribution. Then here I would get the same estimate, which is the product of the marginals. And then I would say, well, are these far enough apart that it can't be explained by chance, like on the basis that I estimated them from these sets of points here? And if so, then I would say, well, yes, there is a significant dependence. But there is one extra thing you need to do, which is as you see more points, you need to make your bins finer and finer. So why is that? Well, imagine that x and y were independent everywhere except for a tiny little point here, okay? So if you use this coarse binning, all of the points over which x and y were dependent might just fall into this square here and you'd never see it. So as you see more points, you need to make your bins finer and finer, because then eventually, with enough points, your bins will be small enough that you'll be able to see, whether x and y are dependent. Because you'll have the right resolution to actually catch that. And you kind of, you have to make your bins finer and finer, but you can't make them finer and finer too quickly, because otherwise you just get 1 point per bin or no points per bin. Most of your bins will be empty. Okay, so you have to be a little bit careful in how quickly you reduce the bin size. So this is again one approach to take, which generalizes the approach that I talked about with the sort of late on time example. The problem is that, again, even with this binning trick, it doesn't actually work very well as soon as your x and y get high dimensional. So in the previous slide, x and y were one dimensional, but I can make a very similar example where x and y each have 4 dimensions. And I do exactly the same. So I have 4 dimensions of x, 4 dimensions of y. I split my 4-dimensional space into bins, like a very coarse binning. And then I use a distance between the joint and the product of the marginals, which you don't need to worry about. And I detect in no cases that x and y are dependent, even though I made an example where they're supposed to be dependent. And this is just because with 1,000 points, when x and y are 4-dimensional, most of my bins are empty, even with the very coarse binning. So I can't detect that x and y are dependent using this classical statistics approach. Okay, so the question that I want to ask now is that, is it possible in these difficult problems, like when you've got text in English and French, or when you've got moderate to high dimensional random variables, is it possible to detect this dependence? So can we somehow represent and compare distributions in high dimensions? So we've got our joint distribution, we've got the product of the marginals. Can we represent them, and can we find some meaningful distance between them such that we can detect dependence between x and y on the basis of this small number of samples? Okay. So this sort of leads to a larger question. So I've talked about dependence detection, where I'm looking at two very specific distributions, which is the joint and the product of the marginals. But a larger question is, I've just got samples from two distributions, and maybe these distributions are high dimensional. Is it possible to somehow compare these? So not just comparing joint and product of marginals, but just pairs of distributions in general. So there are a few examples that we've looked at. So one is microarray data. So you've got samples from microarrays taken from different labs, and you want to know if you can put all the data together and like analyze it jointly. So if the data are from the same distribution, then you can do that because it's somehow the same kind of data. But if they're from different distributions, then analyzing it jointly will give you all sorts of misleading results. And they might be from different distributions because the labs are using different procedures and like they're not aware of these differences. In terms of dependence detection, often you can get random variables that are dependent, but the dependence is very hard to model. But you still want to detect if it's there or not. And then if it's there, you can figure out how to model it. So if you're watching a movie, for instance, and your brain is active, then the link between the movie that you see and the activity in your brain is very complicated. So you might want to test that it's there, like whether some part of your brain is responding without sort of having a good idea of the kind of pattern that you're looking for. Another example of detecting dependence is images and text. So if you've got like images and you're trying to find the text on a web page that describes an image, you can use a dependence measure to find the text that depends on the image. But both text and images, as we've seen, are very high dimensional, so it's a tough problem. Okay, so these are the questions that I'll be dealing with, I guess, in the next 2 lectures. After that, I'm going to so these are all sort of like ways of discovering whether structure exists. Then, rather testing whether structure exists in the data. So whether there exists a dependence or whether there exists some similarity or difference in two distributions. You can then use these measures of distance and these measures of strength of dependence to actually find interesting features of your data. So one example is like find the features in my data set that are most dependent on my labels. So rather than just saying like this image and this caption is dependent, I'm saying this image and caption is dependent because I see in my caption the word dog and I see in some part of my image a dog, for example. Another instance in which we can use this to discover structure is in low-dimensional visualization. So I'm sort of saying, well, give me a very simple representation of my data that nonetheless is very dependent on the original data set, so that captures most of the structure of my original data set. And then this is kind of the opposite problem. So blind source separation is an instance where you have like maybe a lot of signals observed simultaneously, and you're trying to sort of pull them apart and find as many independent signals as possible. So a very classic example of this is if you've got a microphone array in a room and you've got like maybe 3 or 4 people having a discussion, like separate discussions, you want to pull apart those voices and then get like the individual separated sources. So yeah, the Xbox Kinect, for instance, has some blind source separation built into its voice sensor, so it can separate your voice from like what's going on in the room. So these are all the kinds of questions that we'll be using kernel methods in the next few lectures to address. Okay. So I guess in the following lecture, I'm going to talk mainly about, I guess, the most fundamental tool that can sort of solve this category of problems, which is just a kernel distance between probability distributions. So let's say you have 2 samples, you want to tell, are they, how far are they apart? I'm going to use 2 different ways to think about this problem. So I've talked a lot about feature spaces. So I'm going to say that 2 distributions are far apart when the expectations of their features are far apart. So like before I talked about features of points, now I'll take the expectations of those features of points, and that's going to give me a feature of a probability. The other way, so as in the first two lectures, there is a link between feature maps and smooth functions, and that will lead to a second interpretation, which is to look for a smooth function that is sort of large where the probabilities are different. So this is not completely clear yet, but I'm going to give lots of examples of that. And finally, when the feature spaces are rich enough, you can show that these feature maps are unique. So the expected feature map for some distribution is unique to that distribution, and so you can use that always to distinguish one distribution from another. So this is the sort of most basic, I guess, ingredient that we're going to use. Then I'm going to go on to applying this to a very sort of specific subproblem, but a very interesting one, which is dependence detection, where your distance that you care about is the distance between the joint distribution and the product of the marginals. And so then I'll talk about this covariance and correlation. So I think chances are that I'm going to probably not get past this first section in this lecture, so it's likely that this will be in next week's lecture, I think. And then I think, in the lectures afterwards, we'll talk about all these different applications. Okay, so kernel distance between distributions. So first of all, I'm going to start by introducing the feature interpretation, because I think that's perhaps the easiest one to think about. Okay, so let's say that you have two Gaussian distributed random variables, and they have different means, and somebody asks you, well, can you tell me whether these Gaussians are from the same distribution or from a different distribution? And so you'd look up Wikipedia or whatever, and you would say, yes, I do a t-test, okay? Which tells me, like, based on samples from this Gaussian, and based on samples from this Gaussian, are the means far apart that it can't be explained by chance, or it's unlikely to be explained by chance? And if so, then I conclude that these two Gaussians are different, okay? So very old statistical result. Now what happens if I have two Gaussians with the same mean? And somebody says, well, can you tell me if these are different or not? So doing a t-test is going to tell you nothing, but nonetheless, there is obviously a difference between the two Gaussians. So in this case, rather than looking for the difference in the expectation of the variables, so the difference in the means, I'm going to look at the difference in the expectation of some nonlinear feature of the variables. So in this case, because they're Gaussians, the only moments of interest are the mean and the variance, and so a very natural nonlinear feature to consider is just the square of the random variable. Okay? So here is the distribution of the square of x for p in red and q in blue. And you can see now that the expectations of these two nonlinear features are indeed different. So this is the expected x squared for p, expected x squared for q. Okay? And these density functions are chi-squared density. So this is the density of a squared Gaussian random variable. Okay? So you can again do, like, once you know that this feature is a useful feature, you can again use a classical sort of statistics approach to determining that these two means are far enough apart, or whether these two means are far enough apart that it can't be explained by chance. And if so, then you can conclude that P and Q are different. Okay? So the problem with this, of course, is that now I've got two random variables with the same mean and the same variance, so now what do I do? And so you could say, well, I'll find another nonlinear feature, and that's true, but then you're sort of playing at guessing nonlinear features, because, like, whatever nonlinear feature you choose, then somebody's going to come up to you and say, yeah, but what about this case? So this approach at least will work as long as you know in advance what difference you're looking for, but it can be a bit of a dead end if you're not told in advance what you're looking for. Okay? So next we're going to basically take this idea of nonlinear features and think about what that means in terms of reproducing kernel Hilbert spaces. Okay? So just a reminder of the notation that we've introduced in the first lectures. We've got some feature of x. So for this difference of Gaussian's case, a useful feature might just be this two-dimensional vector, which is x and x squared. And remember that we have a representation of a function in this feature space, which is as a sort of set of coefficients such that you can take the inner product of this vector with these nonlinear features to evaluate the function at x, okay? So when I use f dot, or sometimes I use f without a dot, I just mean this vector of numbers. And when I use f of x, I mean that I've taken the inner product of this vector of numbers with the vector of nonlinear features, okay? So this is my notation. And so now, what does this mean? Well, let's say that you have a random variable drawn from some distribution p, and you want to take the expectation of some function in the RKHS of this random variable, okay? So what does that mean? Well, you've got the expectation under p of the inner product of my f representation with my vector of random features, so these are now random variables, okay? So a and b don't have any dependence on x, okay? So I can take my expectation inside that and get the inner product of a and b and the expectation of x and x squared, okay? And I'm going to denote the expectation of a vector of nonlinear features by mu p, okay? So what's interesting is that I've shown that if f is in a reproducing kernel Hilbert space, then I can express the expectation of f as an inner product of my f representative and the expectation of my nonlinear features, okay? So this is fine in finite dimensions. There are, I guess, two problems that arise when thinking about, I mean, even in finite dimensions, we already run into a little bit of a problem. So some random variables don't have certain moments that exist. So the student t distribution, for instance, for some parameters, this thing here blows up, it's infinite, okay? So you might think, well, you know, first of all, how do I know that my expected feature map exists? Like the feature map might exist, but as soon as I take its expectation, it might blow up and have infinite norm. And then this problem might also arise in the case where, you know, you've got an infinitely long vector, so each of the expectations of the individual features exists, but, you know, can I be sure that the, you know, this entire vector, if I take the expectation of each entry, still has finite norm, okay? So you can still sort of take the inner product of f and this thing and it won't blow up to infinity. Because if any of these things happen, then we run into problems, okay? So is that problem clear to everyone? Yeah? Okay, so the difficult answer to that problem would be to like sort of carefully engineer your features to make sure that they all existed, or that their sum of, you know, their norms existed for the random variables that we consider. But there's actually, because we're working with kernels, a theorem which allows us to take a massive shortcut and determine whether, you know, the expected feature map is in the RKHS. You can use it to take inner products, and it has finite norm, okay? So to describe this shortcut, I'm going to first of all describe a property of operators, which is boundedness, and then I'm going to use that property as a way of ensuring that there exists something like this mean feature map, and that it has finite norm, okay? So boundedness, so this is some, A is an operator acting on some element in the reproducing kernel Hilbert space, so this is our function. And boundedness means that this action can always be upper bounded by some number times the norm of the function that it's acting on, okay? So this property, at least, I'm introducing in the abstract here. We're going to see very soon a specific example of it, which is in the case of the mean embedding, okay? But if this property holds, then you are guaranteed that there is some element in the RKHS that allows you to make this operation happen as an inner product, okay? So, you know, if the operator acting on f is bounded, then there will be some function such that you can express the action of this operator as an inner product. And so you can kind of see where this is going now, because, well, one operation you can apply to a function is to take its expectation. So if taking the expectation is a bounded operator, then you can express this expectation as an inner product of the feature map of f and some object which, you know, is the representer of this expectation. So this thing here is exactly the expected feature map, okay? So as long as boundedness holds, then there is an expected feature map, because this theorem tells you, okay? So can we show that this is true? So it turns out that this holds for the expectation as long as the expectation of the square root of the kernel is less than infinity, okay? So the reason for this is that, okay, so we want to say that if this is true, then the expectation operator is bounded. So let's show why this is the case. So our A operator here is now this operator, which I'm going to write as TP. So it takes P, it takes F, and then it takes your expectation of F, okay? So this operator here is the expectation of F, right? Now I'm just going to upper bound this by taking expectation of absolute value of F. So this is just a convenience. Remember that F is the inner product of the function in the RKHS and the feature map, okay? And then by Cauchy-Schwarz, I can upper bound this inner product as the product of phi of x and itself, right? And the norm of F. So this is using this result that inner product of A and B is less than or equal to the norm of A, norm of B. Okay, and the norm, so the norm of phi x, what's that? It's the square root of the inner product of phi x and itself, right? And the inner product of phi of x and itself is just the kernel between phi x and itself. Okay, so this is why we're getting the square root of the kernel here, and then this norm of f is just, yeah, the norm of f. Okay, so this is quite neat, because what we've shown here is that the action of this operator is upper bounded by the expectation of some number times the norm of f, okay? So let's remember f doesn't depend on x, so the expectation here is only taken over this thing here. So now I've shown exactly this boundedness property, because the expectation of this kernel is my lambda here, okay? So that means that as long as the expectation of the square root of the kernel is bounded, then the operator, which is the action of taking the expectation, is bounded. If the operator is bounded, then by Ries, there exists some element in the RKHS such that taking expectations is the same as the inner product with that element. This element here then has to be, by the previous slide, the expected feature map. So basically, as long as the square root of k is bounded, then the expected feature map has finite norm by this chain of reasoning. So are there questions about this reasoning so far? Okay. So I've now said that this mean embedding is a function in the reproducing kernel Hilbert space that allows you to take expectations of f as inner products. Okay, so this is the expected feature map that exists as long as square root of kernel is bounded. Now, because this is in the feature space, you can actually plot it as a function of x. Okay, so this is basically like a long vector of expected features. I can take the inner product of this long vector with the vector of features of x, and I can plot this as a function of x. Okay, and what this looks like is basically the expected kernel between x and like this is basically the convolution of the kernel with the probability. Okay. So this at least I hope makes some sort of sense. So you have basically the inner product of the expected feature map with the feature map at x. So you're basically like taking the expectation with respect to only one of the arguments, which is the argument for the expected feature map. Okay. So that means that I can also, if I have a sample, I can actually make a plot of this function, which is I just replace my expectation with the empirical expectation. So the average of these kernels centered at these sample points. So what does my feature map look like? Well, let's say that I have x here, which I've drawn from a histogram. Okay. And now my expected feature map, I just basically use the samples from this histogram to take the expectation of the kernel function, and I just get a smoother version of this histogram. So this is in the case where I'm using a Gaussian kernel. If I were using maybe a polynomial kernel, then I would get something else, okay? But for the Gaussian kernel, this expected feature map just basically looks like the expectation of the kernel function. So basically like a smoothed version of the distribution, okay? So this is the feature mapping interpretation. So now, as in just the standard kernel methods, there is a link between the feature map idea and the idea of smooth functions. So I'm going to briefly leave aside this idea of expected feature maps, and I'm going to move to like a way of looking for differences in distributions in terms of smooth functions, and then I'm going to show that these amount to the same thing, just as they amounted to the same thing for regression and so on. Okay. So the intuition here is that, let's say that I have a sample from P and Q. So I have these red points I've sampled from some distribution P, they're real valued. The blue points I've sampled from some distribution Q. And somebody asks me, well, are P and Q from the same distribution? So if I just saw this on a plot, I would say, well, that's pretty unlikely that they're from the same distribution. Okay? Sorry, it's pretty likely that they are. But if I saw something like this, then on the basis of this plot, I would conclude that it's pretty unlikely that P and Q are from the same distribution. So it's, sorry, it is, I'm confusing myself. It is likely that they are from the same distribution. And the reason is because, I mean, you know, maybe it's just some very strange pathological things. And maybe there's a lot of mass from P here and a lot of mass from Q here, and like, if you saw a lot of points, you get like a spike here and then a downward spike there. But, you know, at least on the strength of the samples that you've seen here, you know, they both look like they're more or less uniformly distributed across the line, okay? So what I want to do now is to capture this intuition that these are far apart and these are close in some sort of mathematical way, okay? So how do I do this? Well, one way to do this is basically to look for a smooth function which maximizes the difference in expectations under P and Q. So this is why I call it the maximum mean discrepancy. It's a function that maximizes the difference in means. So what does this mean? It means that I'm looking for some smooth function that has large positive amplitude on the points from P and large negative amplitude on the points from Q. Okay, so I've plotted like an example smooth function here. So you see it has large positive amplitudes on the points from P, large negative amplitude on the points from Q. And you can see that, you know, because it's very negative on the points of Q and there's a minus sign here, this is going to make this distance large. Like it will create a large positive number here. Okay, and if I use the same set of smooth functions to maximize the difference in expectations, because of this smoothness constraint, this function can't get very large over these points, and it can't get very small over these points, okay? So this difference in expectations is not going to be very big for this set of points here. So at least according to this distance measure, P and Q here are close together, but P and Q for this example are far apart. Okay, so if I've got a good set of smooth functions, then this idea captures perfectly what I want to achieve for this kind of example. Okay. If instead of having smooth functions, I had functions without a smoothness constraint, so here I'm using just functions that have to be bounded and continuous, so they're not allowed to go above 1, and they're not allowed to have discontinuities, but apart from that, they can be completely arbitrary. Okay, and if I used those functions, then I would say that these points are equally far apart as these points. And so all I would be able to say on the basis of this set of smooth functions is, are the points in the same place, or are they in different places? And that's kind of a very trivial and not very interesting thing to test. Okay? So smoothness matters, basically. Okay? So if you remember, we had earlier on a example where you were trying to distinguish a Gauss distribution from a Laplace distribution. And for this problem, this approach works, because it will tell you that they're different. And you can see that my smooth function here has large negative amplitude, where Q is bigger than P. It has large positive amplitude, where P is bigger than Q. And so if I take this difference in expectations using this smooth function here, I'm going to get a number which is like reasonably large. And so it's going to tell me that the distance between these two is reasonably large and not 0. Okay, so is that example clear? Yeah. Okay. So I talk about, like, there's this set of smooth functions. Well, what is actually a sensible set of smooth functions? We've already seen one that doesn't work. So bounded continuous functions have the property that this difference in expectations is indeed 0 only when P and Q are the same. But the trouble is that when you take finite samples from P and Q, it just says, like, it's a binary thing. It says either they're different or they're not. And that's, like, pretty boring. So there are a number of sets of functions which have smoothness constraints, some of which I guess quite well known in the statistics literature. So functions of bounded variation 1 are one example. So if you use these functions, what this distance amounts to is getting the cumulative distribution function of P and Q and finding the biggest distance between them. Okay? So that's a statistic. The trouble is that when x and y are in more than one dimension, it becomes very hard to compute it. Another set of smooth functions are the bounded Lipschitz functions. We have found ways of computing them in more than one dimension, but they can also be a little awkward to deal with. But in computer vision, these are quite popular, but with histograms rather than necessarily with continuous value variables. So we're going to be using reproducing kernel Hilbert spaces as our set of smooth functions. Now, we will consider, I think, or we will emphasize one particular kind of reproducing kernel Hilbert space, which is going to be called a characteristic reproducing kernel Hilbert space. So this is a Hilbert space which is like rich enough that there's infinitely many features in it, and we can guarantee with this Hilbert space that this distance here is 0 only when P and Q are the same. So it's a way of saying that the reproducing kernel Hilbert space can distinguish any two distributions. Okay, and I'm going to talk later in the course about ways of making sure that my reproducing kernel Hilbert space has this property. So it turns out it's actually not too hard to check. We've seen a lot of reproducing kernel Hilbert spaces which are infinite dimensional, so you can guess that a lot of these are going to have this property. And you can prove, I think, without too much trouble that this is true. Okay, so just a reminder, so I'm going to now tie together the idea of feature maps of the random variables with this idea of looking for smooth functions that I guess have large amplitude where P and Q are as different as possible. So to do this, I'm going to remind everyone of the link between feature maps and smooth functions. Okay. So remember, when we have a function in a reproducing kernel Hilbert space, we can express this as a linear combination of these kernels. So for the Gaussian RKHS here, I've got this smooth function. I've shown in red the kernels that make up that smooth function, and their amplitudes correspond to the weights that I have put here. Okay, so this kind of function is exactly the kind of function that I'm using here. I'm using precisely a function in a reproducing kernel Hilbert space with a Gaussian kernel, okay, to get this smooth function. Okay, so how do I link this with features? So you might remember, if you have a feature map of perhaps a two-dimensional variable, which in this case is this three-dimensional feature map, x1 squared, x2 squared, x1, x2, then the inner product of these two feature maps can be written as a kernel function, which in this case is the squared standard inner product. And remember that a kernel times a kernel is still a kernel. Okay. Remember also that we had an instance of an infinite dimensional feature map. So this Gaussian feature map, which is the Gaussian with one of its arguments fixed, and that we have shown a reproducing kernel Hilbert space where the inner product between these two Gaussian feature maps is just a Gaussian kernel with one of its arguments set at x and one of its arguments set at y. So the kernel where the argument is the distance between x and y. Okay. So given that kernels are inner product of feature maps, you can write this f function here also in terms of feature maps. Okay. So you've got your function, which is a linear combination of Gaussian kernels. We saw on the previous slide that these Gaussian kernels can be written as inner products of feature maps. So this is the feature map at xi, where you're centering your kernel. This is the feature map at x, which is where you're evaluating your function. Okay, and that means that because of linearity of the inner product, you can write this as the inner product of the feature map of x and this f dot. Okay, where the f dot is the linear combination of the individual feature maps. Okay. So given that we can write our functions in feature space like this, we can then find that this idea of looking for a smooth function that has large amplitude when p and q are different is exactly identical to looking for the distance between expectations of feature maps. Okay? So this is what we're going to do on this slide. So this, I think, is perhaps, the most important reasoning for the present lecture. Okay, so here is my maximum mean discrepancy. Okay, so let's see. I'm going to take the square of it just to make the math easier. Okay, I'm looking for a function from some set of smooth functions that maximizes the difference in expectation under p and q. So that's my smooth function here. Okay. Now remember that these functions are in reproducing kernel Hilbert spaces, okay? So that means that from a couple of slides back, I can write the expectations of these functions as inner products between the vectors, the feature vectors that represent these functions, and the expected feature vector under P, okay? So the expectation of the feature map under the distribution P, okay? So let's take this result here and substitute it into here, okay? So now I've got the inner product of f and the distance between the expectation under P of the feature map and the expectation under Q of the feature map, okay? So at this point, I'm going to clarify or give a little bit more detail about the set of smooth functions that I'm using here. So these are in a reproducing kernel Hilbert space. I'm going to actually I'm going to restrict them to only part of that reproducing kernel Hilbert space, which is a set of functions which have norm less than or equal to 1. So this is like a ball in the space. So let me draw that. So I'm saying basically like here is my space. This vector here is my mu p minus mu q, okay? And I'm saying that I'm looking for a function with unit norm, so it has to be inside this ball, right? That has the largest possible inner product with the difference in expected feature maps. So this is expected feature map under P minus expected feature map under Q. Okay? So that's mu P minus mu Q. So what you can see from this drawing, like if I'm in this ball and I'm trying to find the F that maximizes the inner product with this thing here, then what's that going to be? That's going to be the F that's in the same direction as mu P minus mu Q. Because if I rotate this F around, then the dot product with this is going to be smaller. Okay? So I want a unit vector in the direction of mu P minus mu Q. So that means that the function that solves this is going to be mu P minus mu Q divided by its norm. Okay? Because this is exactly this vector here. So if I take the inner product of F and mu P minus mu Q, what I get is mu P minus mu Q, mu P minus mu Q divided by the norm. Okay, and the inner product of something with itself is just the norm squared. This is the norm, so then I end up with just the norm of mu P minus mu Q. So this business here is equal to the norm of mu P minus mu Q. So is that clear, this reasoning here? Are there questions about it? Yeah. So given this, what I'm getting down here is just the square of the norm of mu P minus mu Q, because I've got a square here, so that goes through. So yeah, so this is basically what I've shown here, is that looking for a function, a smooth function that maximizes the distance in expectations under P and Q, if this function is from a reproducing kernel Hilbert space, this is exactly the same as looking at the norm in the difference in expected features under P and Q. Okay? So these two ideas that I've sort of started the lecture with are exactly equivalent in this case. So is that all clear? Are there questions about this? Okay. So the next point is I've described, I guess, two ways of looking at differences in probabilities, and both of them at least seem reasonably complex, because on one hand I'm looking for a function in some huge function space that maximizes difference in expectations. On the other hand, I'm looking for the norm of the difference of some expectations of infinite features, so it seems that I've taken one intractable problem and replaced it with another one. So my next question would be, like, if someone gives me samples from P and Q, can I compute this distance in practice? Because I want to know, like, you know, if it's big, if it's small, like, what is it like? So it turns out that, in fact, it is quite easy to compute. So hopefully, I've already hinted at this in the first lecture, I think, but I'll remind everyone. So remember, I'm looking for the norm of mu P minus mu Q squared, okay? And we've just seen that that's just mu P minus mu Q, mu P minus mu Q, okay? And then I'm going to expand this out, mu P plus mu Q, mu Q minus 2 mu P mu Q. Okay, so these guys here are just the expectations under P of the feature map of X, expectation under P feature map of X, plus etc., etc., etc. Okay, so this expression here, does someone want to guess what it turns into? So the inner product of the two expected feature maps of X. So we know expected feature map of X, map of X dash, that's kernel. So now I've taken expectations. So
expectation of the kernel?
Under, exactly, so I've just got the expectation under P, and here I'm using a rather tricky notation, which is P dash of the kernel of X and X dash. So what do I mean by P dash? P dash means that X dash, which has a distribution P dash, is the same distribution as P, but an independent copy, okay? So what the reason for this, imagine, let's just take a very simple example where the feature map of X is just X, okay? So then what would this be? This would be the expectation of X times the expectation of X, right? Which would be the expectation of the product of X and an independent copy of X, okay? But it would not be the expectation of X squared, right? Because expectation of the product of the means is not the expectation of the square of the variable. I mean, that's, yeah, otherwise the variance would always be 0. So I'm doing exactly the same as I did here, but now in feature space. So I've basically got the expectation of the inner product of the expected feature with the expected feature, but I need to make sure that I keep the random variable here independent of this one. And so that means that I need to use an independent copy of X here, okay? So that I don't make this mistake here. Okay, so is that clear to everyone why I need an independent copy? Yep. Okay, so I've got expectation of P and an independent copy, and then I've got the same thing here, E, Q and Q dash of K, X and X dash. So now X is from Q here, X is from P here. Actually, what I'm going to do is I'm going to make this a Y. So I'm going to say that Y is a variable drawn from Q and X is a variable drawn from P. So Y, Y dash. Then I've got minus 2, E, P, Q, K, X, Y. Okay, so I hope people can see that. Yeah. Okay, so that's now my expression. And you'll notice now that I've taken this, norm of the difference of these infinite feature maps, and I've just expressed that entirely in terms of kernels. Okay, so expectation of PP dash of a kernel, expectation of a kernel. So everything now that I've written in terms of expectations of kernel functions. Okay. So now let's say that I have a sample. I have to erase, unfortunately. So let's say I have a sample now from P, xi, I equals 1 to m, and this is drawn from a distribution P. Now let's say I want to compute the empirical expectation of kx, x dash. So does anyone want to guess what this might look like? So the trick here is to remember that these two have to be independent, and that these are all drawn independently from P. So I will give a, so it's basically I equals 1 to m. xj. So what have I done here? What I've done is I've taken the average of a k between xi and xj for every unmatched pair of I and j. So remember, I have drawn these xi's independently and identically distributed from P. I want to take an expectation of K where x and x dash are independent. So what I've done here is I've taken an average of all possible pairings of these variables except for the case where xi matches with xi. So it's basically like xi and xj for all j not equal to I. Because this is basically an average of all possible cases of these variables such that you're getting k of x and an independent copy of x. So is this trick clear? Why I did this and how it works, yeah? So just like an average of all independent pairings of x that you can get from m points. Okay? So this is how I compute it. And this is nice because now I've basically I have computed if I have a sample from P and I have a sample from Q, I can use this trick to compute the distance between P and Q based on that sample. So now I've got a distance between probabilities. So if anyone has tried, for instance, to compute KL divergence for continuous value variables, you'll know that it can be quite messy. So either you bin your space, which means you get bias, or you do k nearest neighbors estimates, which are very much more advanced, but then a lot harder to actually prove work and harder to compute. Whereas here is a distance between P and Q, which unlike the KL divergence, is incredibly easy to compute and doesn't have any bias problems. So this is something also to consider. Okay, so these are what I've just shown. Yep. Okay, so now let's think about how to detect dependence between two variables. So remember that the dependence problem is the problem of testing the distance between the joint distribution and the product of the marginals. So if joint distribution is equal to product of the marginals, then x and y are independent. If it's not, then they're dependent. So I can do exactly what I did before, but where P is the joint distribution and Q is the product of the marginals. I'm looking for a smooth function that maximizes the distance in expectation between the joint distribution and the product of the marginals. Okay? So here is this example that I started the lecture with x and y scattered in points. And what I've done this, because I need to do it in 3D, so it's a contour plot. I have here basically a function drawn from a reproducing kernel Hilbert space, so it's a smooth function that has largest amplitude where the joint distribution is most different to the product of the marginals. Okay, so this is what this function is here. Okay, and I can make exactly the same line of reasoning as I did before. Okay, so I've got my function from some set of smooth functions that maximizes the difference in expectation over the joint and product of marginals. Then I can write this as basically the inner product of f, the smooth function, and the expectation of the features of the joint minus the expectation of the features of the product of the marginals. Okay, and using again the same reasoning I used in this sort of central slide for the lecture, I can write this, if this function here has norm less than or equal to 1, I can write it as the norm of the distance between the expected feature map for the joint distribution and the expected feature map for the product of the marginals. Okay, so I get exactly the same distance measure, but now P is the joint, Q is the product of marginals. So the independence problem is just a special case of the problem that I've talked about so far. Okay. So there is a peculiarity though, which is how do I actually find a good feature space for this independence testing problem? So if I'm doing two sample testing, like if I want to tell whether P and Q are different for just general P and Q, then I have some objects which are drawn from P, say images. I've got objects which are drawn from Q. There are also images. I've got kernels between a pair of images, and I use the kernels between pairs of images in this statistic here. Okay. But now let's say that I'm trying to find the dependence between an image, which is maybe X, and a caption Y. And let's say I've got like a really good kernel for images and a really good kernel for captions, but now I'm trying to find a feature space on image caption pairs, because I want to know if the pair of images and captions are dependent or independent. Okay. So what do I do? So here is one solution. Let's say this is my kernel on a pair of images, and this is my kernel on a pair of captions. And I want to define a kernel on one pair of images and captions and another pair of images and captions. So I want to say, is this image caption pair similar to this image caption pair? Well, I can just take the product of these two kernels. So if the images are similar and the captions are similar, then this product is going to be large. Okay? If one of the two is small, the product's going to be small. If both of them are small, the product's going to be very small. So this is quite a natural sort of kernel between image caption pairs, at least in this definition. So there might be there are other ways of doing it, but this is one really simple way. If you've got one good kernel for images, another good kernel for captions, then this is a quick way to make a kernel for both. And remember from the very first lecture that products of kernels are kernels, so we know this is a valid kernel. Okay? So we can use this kernel to make a reproducing kernel Hilbert space, which we can then use to find a function that maximizes difference in expectation under the joint and product of marginals. Okay? So this is how we do this independence testing problem. Before I go, and I remember now that I forgot to say one thing, which is I just wanted to give quickly an intuition for this distance here. Okay, so remember I've got basically my distance between samples from P and Q is basically like my, my average over all disjoint pairs of X's drawn from P, average over all disjoint Y's drawn from Q, and then average over all kernels between pairs drawn from Q and pairs drawn from P. So if you think of a kernel as a similarity measure, what does this expression represent? Well, this represents the average similarity between points from P and other points drawn from P. And this is the average similarity of points from Q and other points drawn from Q. And then this thing here is the average similarity of points from P to points from Q, okay? So if on average, the similarity between P and itself and between Q and itself is equal to the similarity between P and Q, then all of this cancels. And the more points you get, the more these similarities will approach each other. So just this is just a nice intuition as to why this is a reasonable distance between P and Q. It's just basically saying, well, if the similarity between points from P and itself is the same as the similarity between points from P and Q, then it's pretty likely that the points from Q are also drawn from the same distribution P. So you've got a set of pictures of dogs, you've got a set of pictures of something else, but if those something else's are just as similar to the dogs as another dog would be, then the Q are going to be also dogs, very likely. So is that intuition clear? Because yeah, I find that just a nice way, without going through the sort of difficulties of feature maps, of sort of seeing that this statistic makes sense. It's a very simple measure of whether points from P and Q are the same distribution. Yeah. Okay. So here is my dependence measure. So here I've just done exactly what I did before, but using as my kernel the product of kernels on the one random variable and the kernels on the second. So kernels on images times kernels on captions. Let me check the time. Okay, yeah, I can start with this. So one of the, I guess, most important things when you're choosing your kernel to do independence testing, to do two-sample testing, and so on, is that you should be pretty sure that your distance is 0 only when P and Q are the same, if you're doing testing of two samples, or if the joint distribution is equal to the product of the marginals in the case where you're doing independence testing. So the way that we choose our kernels to have this property is to make sure that they have this characteristic property. So I'm going to basically say, I'm going to define by characteristic kernels those kernels for which this very strong property holds. Okay? And I will now sort of talk about how to test whether kernels actually satisfy this property. Okay? So characteristic kernels are the kernels for which this distance between expected feature maps is 0 if and only if P and Q are the same. So in other words, the feature maps uniquely represent probabilities. Okay? Now, what we've seen already from classical statistics, there is a class of functions for which P and Q is 0 if and only if the expectation of every function in that class of P and Q are the same, and these are the bounded continuous functions. So remember, bounded continuous functions were not terribly useful in the case where we're trying to distinguish P and Q from samples, because on the basis of samples, if you're using bounded continuous functions, they're basically only telling you whether the points are in the same place or not, and nothing else. Okay? So this set of functions on its own isn't terribly useful. Where it's useful is that certain reproducing kernel Hilbert spaces are able to get arbitrarily close to bounded continuous functions. Okay? So they're able to represent these bounded continuous functions with small error, even though they have a smoothness constraint. And you can then use this property to determine that for these sets of functions, this MMD is 0 only when P and Q are the same. Okay? So this is, I'm bringing this up at first because it's the easiest one to prove, but I'll also flag at this point that it's a pretty restrictive class of functions, because what I'm requiring is that X, the domain on which you're defining your kernel, is compact. Okay? So that means like a lot of kernels you want to define on the real numbers, on RD or something like that. And this argument here will not work for this case because RD or R is not compact. Okay, so it extends off to infinity. But nonetheless, you can make an argument for the compact case, and then later on we're going to talk about, I think, perhaps a more interesting case where X is not compact. Okay. So, in a sense, also we're taking advantage of the hard work done by someone else, because I'm saying, like, I can prove that if somebody gives me a kernel that's universal, then I can show that it's characteristic. But then, like, a pretty natural question might be to say, well, okay, you've taken one definition and you've shown that if that definition holds, then another one holds. But how do I show universality? And that's also a reasonable question. And to show universality is actually not trivial. Fortunately, the hard work has been done for us, and a number of people have shown that, for instance, the Gaussian kernel is universal. So if somebody has done this hard work for you and has given you a universal kernel, then you can say, well, I can conclude that that kernel will have this nice property and I can use it for testing. But what you might want to sort of more reasonably ask is, well, what if I don't know if a kernel is universal? What if someone just gives me a kernel? Can I immediately test this property? And that's what I'll sort of talk about later, but that's a slightly harder question to address. Okay. So the fact that universality implies characteristic is actually really easy to show. Okay. So basically, I'm going to show that we'll like both directions of the proof. So if the kernel is universal and MMD is 0, then P is the same as Q. Because the other direction is trivial. Like if P and Q are the same, then the expectation of any function under P and Q is the same. And so the expectation under reproducing kernel Hilbert space functions of P and Q are the same. And so this is 0. So it's like a very boring statement to make. But the other direction is much harder. So what I want to show is that if the distance between the feature maps is 0, then P and Q are the same. And that's where like the work is going to happen. Okay. Okay. So universality of F, as I've said, what it means is that you can, for any bounded continuous function, so here is a bounded continuous function, I can find a function in the reproducing kernel Hilbert space such that like the largest gap between these two is smaller than any number that I choose. Okay, so this is what I mean by denseness here. Okay, so basically like if I've got, so I might have a bounded continuous function, which is like, you know, quite spiky, but then I'm saying that there is a reproducing kernel Hilbert space function which basically you can get a smooth function where the largest error, so let's say this is the largest error, is smaller than epsilon. And you can sort of get a smooth function that's arbitrarily close to this sharp function here. So I'm saying that my reproducing kernel Hilbert space has to be rich enough for this to be true. Okay, so the largest error you're going to make is epsilon. So is that clear? Yeah? Okay, so given that I have a function in my reproducing kernel Hilbert space, whose largest error with respect to the bounded continuous function is epsilon, what do I do then? Okay, so basically, here is my difference in expectations of a bounded continuous function. Okay, so this is my f. What I can do is I can basically add and subtract this good reproducing kernel Hilbert space function from it. Okay, so I'm basically like adding and subtracting the expectation under p of this nice function, and I'm adding and subtracting the expectation under q of that nice function, and then I'm basically doing an upper bound by splitting these absolute value terms into the sum of a whole bunch of terms. So this is just using the result that a plus b is less than absolute a plus absolute b. So that's the result that I'm using to make this upper bound here. Okay. Now, because of this property here, I can be sure that the expectation under p of f, which is my bounded continuous function, and of g, which is the RKHS function, which is very close to it, these expectations have to be less than epsilon. And this makes sense because like if the largest distance between f and g is epsilon, then in expectation, for sure the difference is going to be smaller than epsilon because the biggest possible distance between them is epsilon. So, you know, the expected distance between them, or the distance between their expectations, has to be smaller than that. Okay, because like the epsilon is like the worst possible distance between the two. Okay, so I'm saying that this is going to be less than epsilon, and this is going to be less than epsilon. Okay, because of this property here. Okay, so what am I left with? I'm left with this middle term, which is the expectation under p of g minus expectation under q of g. And g is a function in the reproducing kernel Hilbert space. Now the thing is that the expectation under p of g minus expectation under q of g is just the inner product of g and the distance in the expected feature maps. We've shown that. But we know, because the MMD is 0, the distance between the expected feature maps is 0. Okay, that's what we've assumed, like that's what we started with. So that means that we know that this is 0. Okay? So let's go back to the previous slide. So I know that this is less than epsilon. I know that this is less than epsilon. I know this is 0 because this is 0. Okay? So that means that my difference in expectations of these bounded continuous functions under p and q is less than or equal to 2 times epsilon. Okay? And this is true for all of the bounded continuous functions. And this is also true whatever epsilon I choose, this has to hold. Okay? So because it's true regardless of how close this gets to 0, I can conclude that basically the difference under the expected difference under p and q of this function, this bounded continuous function, is going to have to be 0 for all p and for all f in the bounded continuous functions. And so that means that p and q are the same, because that's the mathematical fact we started with. So basically, what I can show is that as long as as long as the distance between the mean embeddings is 0, and as long as my feature space is rich enough that I can get close to these bounded continuous functions, then I can be sure that if the distance in expected feature means is 0, then P and Q are the same. Okay. So is this argument clear? Yeah. So basically, like, this is kind of a nice property as long as somebody tells you that you can get close to the bounded continuous functions. So if you can get close to bounded continuous functions, then you can make that argument. And if you sort of do a search for universal kernel, there are a lot of papers in the literature which actually go and prove certain kernels are universal. So if your kernel happens to be one of the lucky kernels, then you can just plug this result in and say, well, if I use that kernel, then I can distinguish probability distributions. If the distance is 0, then P and Q are the same. Okay? So yeah, this is kind of a nice result, but it's also a result that relies on other people having done, I guess, the tough work. So this one, I'm going to just give a hint of how this proof will start, and then I'll resume it, I guess, next lecture, because we're short of time. So my next point is, well, first of all, universality has been shown for compact domains. So if you're on a non-compact domain, then this argument becomes a lot harder to make. But I think more to the point, if somebody gives you a kernel, you shouldn't need to rely on someone else having proven universality to determine whether the kernel is characteristic or not. And it might be that you can actually show directly that a kernel is characteristic. Okay. So what I'm going to do is I'm going to show this for the translation invariant kernels, which are the kernels which take as their argument the distance between the 2 points, or the difference rather between the 2 points. And I'm going to use a specific result which I talked about in the first 2 lectures, or I was hinting at in the first 2 lectures, but now I'm going to sort of make explicit. So if you have a translation invariant kernel, then this can be written as the Fourier transform of a non-negative measure. So remember, in the very first lecture, I gave an example of a Fourier series for a Gaussian. So if you had a Gaussian on a periodic domain, so here is like a periodic domain minus pi and pi, and let's say you have a Gaussian kernel on this domain. Okay, so this is the k. So this argument here is the distance between x and y, and this y-axis here is the k of x minus y. Okay, so this is my Gaussian kernel, and when I took the Fourier transform of this Gaussian kernel, I got also like a Gaussian shape. Okay, and it's a Fourier series, so here it's discrete valued, but I can generalize it to get a Fourier transform for continuous in the case where this is no longer periodic. Okay, but the important thing is that the Fourier representation of this Gaussian kernel has no negative coefficients, and it's when you sort of sum everything up, it's finite. Okay, or if you integrate it in the continuous case, it's finite because you can take the integral of a Gaussian. So basically, any kernel can be written in this kind of representation as a Fourier transform of something that's never negative and that is always integrable. Okay, so the Gaussian is one example, but every kernel has that same sort of representation. Okay, and the second trick that we're going to use is that if you take the expectation of the kernel under some probability, you can represent this in the Fourier domain as a product. Okay, so I'm going to give an illustration on the next slide, but just to give the theory result first. If you've got the expectation, the expectation of x distributed according to P of the kernel of x minus x dash. Okay. This can be written as the Fourier transform, or the inverse Fourier transform in this case, of the product of the Fourier transform of k. Okay. So let's say I've got a Gaussian kernel. Actually, so this can be written as the product Fourier transform of k with the Fourier transform of the probability measure, okay, which I'm writing here as the characteristic function, okay. So this is, like the second representation. So I think the best way is to show this with an example, I think, okay. So let's say that I've got P, which is a Gaussian, and Q, which is a Gaussian, which has had like small wiggles added to it, okay? So I can represent these in Fourier terms, basically as the sums of, or in this case, integrals of sinusoids of increasing frequency. So the Fourier transform of a Gaussian, we already know it's just a Gaussian. The Fourier transform of this Gaussian with wiggles added to it looks like a Gaussian with these two bumps on each side of it. So what are these bumps? These bumps occur exactly at the frequency of these wiggles, okay? And this makes sense because, like, remember, you're building up this distribution as a sum, effectively, of sinusoids of all these different frequencies. And I've said that, like, a really important part of this distribution is these sort of wiggly perturbations at a particular frequency. So I would expect when I'm building this thing up in terms of sinusoids that I would see these spikes on each side corresponding to these oscillations. And that's exactly what I see here, okay? So I've taken now the Fourier transform of the distribution P. I've taken the Fourier transform of the distribution Q. Now, I'm going to subtract these two Fourier transforms. And now all that I'm left with is the Fourier representation of these wiggles, okay? So these sort of two spikes, which are centered at the frequency of the oscillation of this thing that I've added to my Gaussian here, okay? So if my goal is to determine whether P and Q are different, this amounts to sort of saying, well, can I see in the Fourier domain that there exists a difference between these two distributions? And so obviously there is. I can see it here. So like looking at a difference in this domain is the same as looking at a difference in that domain, okay? And so now the next point is, so what I was doing before to find the difference in P and Q was looking for the expectation under P of kx dot minus expectation under Q kx, or ky rather, dot. And I was going to take the squared norm of this. So the squared norm of the difference in expected features, okay? Now, using the property that the expectation of the kernel in the Fourier domain can be written as a product, what I get is basically like the Fourier transform of P, so that's this Gaussian here, minus the Fourier transform of Q, which is this wiggly thing with the two spikes, multiplied by this thing here, which is the Fourier transform of my kernel, okay? Then I take all of that, I take the inverse Fourier transform, f minus 1. That just gives me back this expression here, and then I take its norm, okay? So basically, this operation here of looking at the difference in expectations of the kernels, if you write it in the frequency domain, it can be just written as the product of the Fourier transform with the product of the difference of the Fourier transforms under P and Q, okay? So if my kernel is a Gaussian, its Fourier transform is a Gaussian, the product of this Gaussian with these two spikes is obviously not going to be 0 because the two spikes overlap with the Gaussian. So then when I take the inverse Fourier transform and take the norm, I'm going to get something that isn't 0. So the Gaussian kernel from this argument is characteristic. So this gives me now the clue that I'm after, which is that as long as my kernel has a Fourier transform that doesn't vanish anywhere, then I'm going to be able to see any difference in P and Q, because when I take this product, it's going to be non-zero. So this gives me like a very easy trick to test whether a kernel is characteristic. You just take its Fourier transform, you look if it's got any holes in it. If not, then you're done. So here is a kernel whose Fourier transform is a top hat function. And this is a valid kernel because, as I've said, like, you know, anything that is a inverse Fourier transform of something which is never negative and which has a finite integral is a valid kernel, okay? But the trouble with this kernel is that if I multiply its Fourier transform by the difference in Fourier transforms of P and Q, it's going to be 0, okay? And so this kernel here is not characteristic because I can create P's and Q's which are different, and yet the maximum mean discrepancy between P and Q is going to be 0. Okay, so I think, yep, I will stop for today, but I will resume, I'll go over this again at the start of next lecture.